Hi everyone, my name is Brian Wan. I'm a second-year master's student at the University of Toronto. In this video, I'm going to present BlinkSync, enabling multimodal smartwatch gestures with synchronous touch and blink. This is a joint work with my advisor, Toby Grossman, at the Dynamic Graphics Project Lab. So, smartwatch has become increasingly popular, yet their limited form factor makes input a challenge. To solve this problem, prior work has tried to increase the receptive area of touch input, or reduce the contact area of touch to increase the precision. On the other hand, eye-based input has been proposed to provide subtle, instant, and hands-free interaction. What you look is what you get. However, human eyes are meant to serve as perceptive organs and did not evolve to be fully controllable. As such, they are prone to false activations. Everywhere you look, another command is activated, namely the Midas touch problem. So, we ask a question: if individual inputs are limited, can we combine them together to solve each other's limitations? Actually, combining eye plus touch input isn't the news. Prior work has investigated how to use these two input modalities sequentially to enable novel interactions. For example, using gaze to select an item, then use touch to manipulate on the tablet. Or in a desktop setup, a user can use their gaze to move the cursor instantly between distant areas on the screen, then use the mouse to fine-tune the selection. However, prior work usually only used eyes to supplement the other primary inputs, and the interactions were mostly sequence-based, such as gaze select first, then touch manipulate. We instead wondered, why don't we let the two inputs complement and reinforce each other's? We hope to use touch to reduce the false activation problems of eye input, and we want to use eye input to augment the touch input when the input expressivity is limited, for example, when using a smartwatch. To do so, we propose the concept of a mutual delimiter. We first start from a delimiter. What is a delimiter? Let's say we have a timeline here, and we have a series of input signals. The use of a delimiter is to delimit a certain interval of that signal where the same input should have different meaning or functions. For example, when you press the Control key and click on items, the clicks will have different behaviors. Then the Control key is a delimiter of the mouse click. So what is a mutual delimiter? Let's say we have signal 1 here, and it's delimited by another signal. And at the same time, signal 2 is also delimited by signal 1. So both inputs delimit each other at the same time to solve each other's limitations. Our goal is then to find out a gesture set that could serve as mutual delimiter to enhance both inputs together. So we first look at a larger design space for eye plus touch input. We can have blink and touch with different durations, such as long blink and short touch. The blink and touch events could also happen in sequence, such as blink blink touch or blink touch. If a pair of blink and touch happen at the same time, then they are synchronized. And we can see there are 3 types of synchronizations here: synchronous start, synchronous ends, and synchronous starts and ends. Lastly, we can have different touch gestures, such as swipe and tap, and different eye expressions like gaze, blink, and wink. Then we narrow down the design space. Firstly, we hope the gesture could be performed rapidly, so we only consider short events. For the same reason, we also didn't consider sequential input. And we did not consider gaze in the gesture design, but it turned out that gaze can be incorporated for some use cases, which I will discuss later. And we discarded winks because it's not easy to be performed for everyone. So, here's the final design considerations. Short, synchronous blink and touch events. We present BlinkSync, a gesture set enabled by performing a pair of synchronous blink and touch on a smartwatch. To perform a blink sync gesture, users simply need to blink and touch on the smartwatch at the same time. Then, we have these gestures. We were curious about how often would this gesture, a pair of synchronous touch and blink, happen spontaneously. To answer the question, we conducted a 12-participant user study gathering blink and touch data during normal use to understand the probability of false activations of this gesture. We designed 4 tasks with different task intensity and platforms. The 2 smartwatch tasks are using calculator and reading newsfeed, and the 2 paper tasks are solving word puzzles and reading articles. We collected both touch and blink data during the study. Here's a breakdown of the rates and durations of the blink and touch. As expected, touch rate is higher for calculator, which requires more tapping to enter formulas, while the touch duration is longer for newsfeed, which requires more dragging to browse news. For both smartwatch and paper tasks, the blink rates dropped when the task intensity increased. The blink durations were consistent across different tasks, but it's a little bit lower for solving word puzzle. It could have been due to a heavier visual workload. And remember that the goal is to find out how often would a synchronous pair of touch and blink happen. And our results show that it's actually rare for users to perform this gesture spontaneously. Here's a plot of the calculated offset. Each dot in the plot is a touch event, with its x coordinates representing the start offset with its nearest blink event, while the y coordinates represent the end offsets. And we can see that the dots are quite sparse in the central region, with only less than 2% of the data points falls within the 250 millisecond threshold. We also found that if we consider both start and end offsets, we'll get a lower false activation rate. Therefore, the final blink sync gesture consists of a blink synchronized with either a tap or a swipe in 4 directions. And the blink and touch events need to be synchronized in both start and end with a 250 millisecond threshold. We then conducted a second study to see whether the users were able to easily synchronize the 2 channels of signals, blink and touch. We compared blink sync with other commonly used smartwatch input techniques for commercial products to understand what's the overhead cost of blink sync gestures. These 2 techniques were touch after pressing a hardware button and normal touch. The results showed that the users can successfully perform all 3 techniques without difficulties. In terms of completion time, blink sync only adds 0.15 second overhead to normal touch, but is 33% faster than pressing the hardware buttons. And we found that the offsets are well within the threshold we set for the study, and it's interesting to see that offset values are lower for the start time, indicating the potential to define separate threshold for the start and end. Combining this data with the results from Study 1, we suggest future implementations consider our chosen offset of 250 milliseconds, which elicited a true positive rate of 97%, while limiting the false positive rate to less than 2%. Blink sync occupies a unique application space where 2 inputs can augment each other's. So let's first start from blink augmented touch input. We developed a mock-up application for Smartwatch Shortcuts on system-level functions, such as calling the main menu or exiting an application. These functions are usually achieved by pressing hardware buttons. However, the number of buttons on a smartwatch is limited. With Blink Sync, we can solve this problem easily. For example, Blink Sync left and Blink Sync right cycles between recently used apps. Blink Sync down terminates the current application. Blink Sync up shows all recently used apps. Another application space is touch augmented blink input, we developed several applications to use BlinkSync for smart environment control, by looking at an appliance and performing a BlinkSync gesture. Here's an example of using BlinkSync to control light. To turn on a light, user look at it and perform a BlinkSync up gesture. A BlinkSync tap gesture changes the light setting. And a BlinkSync down turn off the light. We also explored the idea of retrieving a contextual user interface. If the user looked at a device and performed a BlinkSync gesture, a UI would be extracted from the device to the smartwatch for the user to control. Finally, BlinkSync can be used to transfer information from smartwatch to other displays, such as laptops or televisions. Of course, there are a few issues surrounding BlinkSync gestures. Firstly, the eye tracking technology. In our prototype, the user needs to wear an additional eye tracker glasses, making it less accessible for common users. Fortunately, a Japanese company, Jeans, released a product called Jeans Meim, which looks exactly similar to a common eyeglasses that we wear every day. This makes BlinkSync possible to be used by a wider audience in the near future. Another issue is for BlinkSync to avoid conflicts with normal touch, because there might be a potential following blink after a touch event. The BlinkSync gesture recognizer needs to wait a short time before classifying the event as a normal touch or a BlinkSync gesture. So every touch interaction would have to wait a short period to be executed. To mitigate this, we can classify the gesture right after a touch if the user's eyes are open, and only takes a short pause when the user's eyes are closed. In this way, the users would not even notice that short pause because their eyes are closed. So, key takeaways. We present the concept of a mutual delimiter, where two modalities are used to jointly delimit the intention of each other's input, therefore increasing their respective input vocabularies and addressing any potential issues of false activations. We also conducted two studies showing that it is rare for humans to perform synchronous touch and blink events spontaneously on a smartwatch. But when they really want to do so, they are capable of performing such gestures easily and accurately. Lastly, we developed several mock-up applications exploring the future potentials of how BlinkSync can be used to interact with a variety of devices. We hope our techniques can serve as an important groundwork for future work on multimodal wearable input.